We are live now. Good day to all. A warm welcome to each and everyone present for our SSE E talk series conducted by Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. Today talk will be the 19th talk of the series. I am Dr. Deepak, Associate Dean, International Affairs, Saveetha School of Engineering, Saveetha Institute of Medical Sciences. At the outset, I sincere thanks to our Honorable Chancellor, sir. I also extend my thanks to our Director Madam for Madam's continuous support, guidance, and motivation to conduct this event. I also thank Principal Sir and Vice Principal Sir for their support. Today, we have with us Professor Satoshi Watanabe from University of Tokyo. Dr. Satoshi received his PhD degree in physics from the University of Tokyo in 1989. He worked on the Ano Atom Craft project at the Research Development Corporation of Japan, now Japan Science and Technology Agency from 1989 to 1994, and at the Advanced Research Laboratory Hitachi Limited from 1994 to 1997. Afterwards, he joined the University of Tokyo in 1997 as an associate professor of Department of Materials Engineering and became a professor in 2004. He was the director of Center for International Affairs, School of Engineering 2015 to 2018, and is special advisor to the president and the chair of India-Japan Exchange Activity Strategy Working Group, the University of Tokyo. Among others, he served as editor-in-chief of e-journals of surface science and nanotechnology from 2009 to 2018, and he has been a member of International Organizing Committee of Asian Workshop on First Principles Electronic Structure Calculation since 2011. I am very happy to welcome Dr. Satoshi Watanabe to give his invited talk in our SSE E talk series conducted by Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. Over to you, Dr. Satoshi.
Thank you, Dr. Deepak, for kind introduction. And good afternoon, everyone. Thank you for joining my talk. I'm very glad to have this opportunity to give lecture to you. Okay. So this is the outline of today's talk. Before going into the main topic, I'd like to talk a little about overview of the University of Tokyo and some related issues. Then I'd like to give introduction of today's main topic. First, I'd like to mention the importance of understanding phenomena in novel information devices on the atomic scale. Then I'd like to explain the importance of understanding atom-ion behaviors in such devices. And then I'd like to give a brief overview of first principle simulations for such purposes. Then I'd like to move on to the main topic, machine learning approach combined with first principle simulation data for simulation of atom-ion behaviors in novel information devices and energy devices. So here, I'd like to give an overview of machine learning approaches, and then I'd like to show two application examples. One is atom migration, and the other is lattice vibration and thermal transport properties. Okay, so I hope that all of you know the location of Japan here, and also that Japan is much smaller compared with India, both in area and population. Around here is located the capital of Japan, Tokyo, and University of Tokyo is located here. Okay, so University of Tokyo was established in 1877, and actually quite a big university in Japan. So we have 10 undergraduate faculties from agriculture, atom science, to engineering, to law, to medicine and science. And we also have 15 graduate schools and 26 research institutes and centers. And actually, we have 3 campuses. I'm on this campus, Hongo campus. It is near the center of Tokyo. Besides that, we have 2 other campuses. One is called Komaba campus, and the other is Ashio campus. So actually, in our university, we have about 27,000 students. It's rather big in Japan, and the largest among the Japanese national universities. But of course, I know that in India, you have many big universities. Anyway, among them, about 3,500 international students. And we have 10,000 university staff. And here's a list of Nobel Prize winners who graduated from University of Tokyo. So we are proud of these 10 Nobel Prize winners from our university. And actually, the University of Tokyo have a long relationship with India. So this is not the first one, but a very important event is that the visit of first Prime Minister of India, Nehru, to our university. And this hotel of Tagore is a gift from Prime Minister Nehru. And it is now in our university collection, university library. And Mr. Narendra Murthy, the founder of Infosys Limited, has been a member of Global Advisory Board of our university. And actually, we opened the India office in 2012. This curve shows the number of Indian students in our universities. So the number is 85 in 2017, but now it's a little over 100. But still this number is very small compared with the total number of international students in our university, more than 3,000. So we'd like to have more Indian students to our university. Okay, so as I mentioned that we have India office and it's now in Delhi. And one important point I'd like to mention is that this office is running a project called Study in Japan Global Network Project in Southwest Asia. And this project is supported by Ministry of Education in Japan. And this project is not for only University of Tokyo, but for Japan-India cooperation for all the universities in Japan. So now you can get information on the Japanese universities and also study in Japan, such as study and research in Japan or life in Japan or scholarship and so on from our India office. So if you are interested in, please visit this website. This is the website of University of Tokyo India office. And next, I'm belonging to the Faculty of Engineering and also the Graduate School of Engineering. And the Faculty of Engineering is the largest faculty in University of Tokyo. And now it has 16 departments, as shown here, from civil engineering, architecture, electrical and electronic engineering, applied physics, and also chemical system engineering, and so on. And I'm in the Department of Materials Engineering. And our university has a little bit complicated structures. So relation between the undergraduate faculty and graduate school, it's not straightforward. So that the Faculty of Engineering is related to these graduate schools, Graduate School of Engineering, Frontier Sciences, Information Science and Technology, and Interdisciplinary Information Studies. Anyway, so because of time, I'd like to move on to the introduction, very brief introduction of our department, Department of Materials Engineering. So our department is not so large. So number of faculty is 35. This includes the professor, associate professor, lecturer, and assistant professor. And we also have a joint affiliation faculties. For undergraduate course, 11 such joint affiliation, and for graduate course, 22. So that in total, about 50 or 60 faculties. And for the number of students, for graduate course, undergraduate course, it's about 170. But it includes only third and fourth grade students. In University of Tokyo, all of the first and second grade students belong to the Faculty of General Arts. So this includes only third and fourth grade. And for graduate course, we have 180 students. And among them, we have 52 international students. This includes 4 Indian students. So although the size of the department is not so large, our department covers a wide area. From biomaterials, such as drug delivery system, medicine, or medical devices, to the steel or other metal, or the materials recycling, and from nanomaterials, including communication devices, electronics, and batteries. Okay, so now I'd like to move on to the main topic of today. Okay, so as I mentioned, I'd like to discuss behavior of atoms and ions on atomic scale. So why we are concentrate on this scale? I'd like to discuss on this scale. This is because the length scale of recent devices is just on such a scale. So this is a processor in personal computers, and your smartphone also has a similar kind of processor. And if you look into the inside of such processor, inside is like this. And actually, the many devices. The basic unit is this transistor. So such transistors are included in this small area. So the number is much more than 1 million now. So each transistor is very small, as shown here. So this is about 50 nanometer. By the way, 1 nanometer is 10 to the 9th meter, and this scale is comparable to the size of atom. So the atomic radius of hydrogen is 0.53 nanometer. And in fact, this picture is out of date. Recently, the length scale of transistor is the order of several nanometers. So we have to consider the atomic scale. By the way, this size is already smaller than viruses. So this picture is an influenza virus, but SARS-CoV-2 virus has a similar size. So a recent device is much smaller than bias. Okay. So next, this slide shows the trend of microprocessors. So this shows the number of transistors in one processor. So you can see the rapid increase. The important point is this scale is exponential. So the number of transistors in a processor increases exponentially. So of course that single-thread performance, that means that the performance of basic transistor also increases. And the frequency of the transistor or processor also increases. But as you can see, the frequency is saturated here. So this is quite different from this trend. So why frequency is saturated? Actually, one of the important reasons for this is the heat problem. So Joule heating in processor is quite serious issue. As you may know that when a processor is in full operation, it becomes very hot. So sometimes you can bake egg, as shown here in this picture. So actually, to solve this heat problem is very difficult. Of course, that if the device becomes too hot, that the device cannot work properly. So because of these issues of the clock saturates like this. So to solve this problem, we have to understand Joule heating on the atomic scale. And this Joule heating is strongly related to lattice vibration. So later I'd like to discuss lattice vibration. And this lattice vibration is also called phonon. So I also use this phonon later. Okay. So actually that atomic behavior are also important in another aspect. So in the case of processors and other conventional devices, atom migration often causes degradation of device performance due to, for example, dielectric breakdown and other failure. So this is very bad point of atom migration in a device. On the other hand, in some novel devices, uses positively use such kind of atom migration. For example, I'd like to explain that the resistive random access memory shown here. This device consists of one electrode, metallic electrode here, and insulating layer, and counter electrode here. And by applying appropriate voltages between these two electrodes, conductive filaments grow inside this insulating layer. And when this filament reaches to the counter electrode, the resistance of this device becomes very low. And then if we apply the voltages of opposite direction, opposite polarity, then such kind of filament breaks. Then the resistance of this device becomes much higher. So in this way, resistance switching can be achieved in these devices. And this resistance switching can be used to store memory. So this can work as a memory. So such kind of memory device is called resistive random access memory. Of course, ion migration is very important in energy device, such as batteries. So in the batteries, the charging and discharging process is the most crucial processes, and these processes are caused by ion migration. So we'd like to discuss these kinds of atom-ion behavior in novel devices. So how can we deepen our understanding on such atom-ion behaviors? Of course, we can perform experiments. For example, we can measure thermal conductivity or diffusion coefficient. Such kind of measurement or experiment is very important. But in the very small devices, it's very difficult to measure with knowing the atomic structure exactly. So to deepen our understanding, it's very important to know the relation between atomic arrangement and materials properties. So to observe those in measurement is very difficult. So in such simulations are very powerful. The only problem is that whether the simulation are accurate enough or not. But recently we can say yes, owing to the development of first principles method. The first principles method is a method based on the basic theory and which doesn't use parameters that are determined to fit to experimental data. In fact, such kind of simulation becomes very important in the last a few decades. And this slide shows the paradigm changes in the researches in material science and engineering. Of course, at the first stage, empirical science based on experiment was very important. Of course, it has been important still now. But then that theoretical science has been developed. So we established the basic theories, basic equations such as Newton equations, Maxwell equations, Schrödinger equations, and so on. Then we entered to the third paradigm era, computational science and simulation. And as I mentioned, that first principle simulations is very important on this stage. And there are two important factors for this third paradigm. Of course, first one is the development of computers. So this slide shows the progress in computer performance. So this red line shows the performance of the world's fastest supercomputers. So you can see this unit is petaflops. The flops means the number of floating point operations per second. So, and the petaflops peta means that the 10 to the 15th. So the 90 petaflops means 10 to the 17th petaflops. So this is very fast. But another important factor is the development of method. As I mentioned, that the basic theory has been established. In the case of atomic scale world, the basic theory is quantum mechanics. And the most important equation is the Schrödinger equation. So if we can solve Schrödinger equation, we can know everything, simply speaking. But problem is that the exact solution of Schrödinger equation is not available in most cases. So even for model systems, and even using the world's fastest supercomputer. So we have to introduce some kind of approximation. So we have to develop such kind of approximate method, but with sufficient accuracy. In fact, such kind of method has been developed. So these two professors, Walter Kohn and John Popper, developed first principles method called density function theory for Kohn and molecular orbital theory for Popper. So owing to the development of such method, now we can predict materials properties, many materials properties with sufficient reliability. And because this development of this method very important in the progress of material science, these two people got a Nobel Prize in chemistry. Okay, so here I'd like to show only a few examples of what first principles simulation can do. That is that high throughput screening of materials. So in many cases, we want to have material which is most suitable for some specific objective or specific purpose. So to obtain such materials in traditional way, so first we have to list up candidate materials, then we have to synthesize all of them and characterize or measure the properties of these synthesized materials, then analyze the result, and then pick up the best material. But of course, the synthesis and characterization takes much time. So if the number of candidates are very large, this process needs huge efforts. But because recent first principle simulation becomes quite reliable, now we can predict the properties of materials in silico, means in computer. So after calculating such materials properties, then we can compare such properties and then pick up the best material. Of course, we need a validation process to check that this candidate has really good properties or desirable properties. But compared with this case, experimental effort is much lighter in this case. But in fact, the Japanese group applied such kind of approach to obtain a good cathode material for lithium-ion batteries. Because of time, for details, please look at this paper. Anyway, in this case, they fix some base material and consider some impurities, adding impurities in this base material. And they examined many combinations and determined the best performance impurity combinations. And then also perform experiments and confirm that their prediction was correct. So in this way, first principles simulation is very powerful now, but still there has been some problem. Simply speaking, a first principle simulation needs heavy computations. So the size of simulation model is limited. So in a routine research, the model size is usually several hundred atoms. And as the number of electrons in the model increases, the computational load increases as n squared or n cubed. So because of this scaling, to increase the model system size, it's a little difficult. And if we want to examine atomic behavior, atom migration, or lattice vibration, there's another issue. That is that we can examine such kind of atomic motion by combining simulation method. I mean that Schrödinger equation for electrons and Newton equation for atoms. So by treating atoms classically and electrons quantum mechanically, we can examine atomic motion. But in such simulations, we have to change the atom position small by small. I mean that time has been changed little by little, and this time period is the order of femtosecond, 10 to the minus 15th second. This means that if we examine 1 million steps, this only corresponds to the motion of 1 nanosecond. So this is often insufficient. And in the case of some properties, in fact, first principle calculation of thermal conductivity has become possible recently. This is one example of a paper shown here. This is the thermal conductivity of gallium nitride. And so this is a perfect gallium nitride crystal case. And this is the calculation result, including the correction for isotope effect. And agreement with this corrected curve with experimental data is very nice. But if we want to examine, for example, defects with a more complicated system, including interface, the model size becomes much larger. So the computation becomes too heavy. So basically, if we want to examine the lattice vibration, we have to consider, by the way, this is a Taylor expansion of energy of the system around one certain atomic position. And in the case of lattice vibration, that this coefficient of the second term is very important. And in the case of thermal conductivity, the higher order, third or fourth order, is very important. But if the model includes many atoms, here the number of coefficient becomes huge. So this is the origin of this heavy computation. So in such a problem that first principle simulation is still very difficult. So now the machine learning approach becomes very promising. Actually, that machine learning technique becomes attractive in many aspects of materials researches. And actually, so it is called in many names, such as data-driven approach or informatics or machine learning. All of them are very similar. And actually, they can be applied to various aspects of material researches. In the case of experiments, we can use such approach for first search of optimal conditions for synthesizing high quality films, or obtaining high-resolution images or spectrum using minimum number of data. In the case of simulations, we can accelerate simulations without loss of accuracy. So in my talk, I'd like to show one example of such simulation. Okay, so important point in simulation of atom motion is this relation between atomic arrangement and energy and forces acting on atoms. And to obtain this relationship, there are many approaches. And traditionally, such approaches can be divided into two classes. The one is the first principle one, and as I mentioned, this is reliable, but needs heavy computation. The other is the empirical force field. And for example, the potential energy of the system can be expressed like this. This is one famous empirical force field named called Stringer-Weber potential, and this is very good for silicon. And as you can see that this potential includes many parameters such as this A, B, P, Q, and this lambda and gamma. And these parameters determined so as to agree with some kind of experimental data. But although the computation for such kind of method is very light, but often that the reliability, well, accuracy is very poor. So in machine learning approach, we use machine learning method to obtain this relationship between atomic arrangement and energy and forces. Actually, many methods can be used, neural network or kernel regression and so on. And many kinds of machine learning potential have been already proposed. But here, I'd like to focus on this neural network potential. Anyway, in this approach, first, we prepare first principles simulation data. And then machine learning method is used to obtain this relationship between atom arrangement and energy, so that this relationship in this simulation data, first principle simulation data, reproduced as much as possible. And in the case of neural network potential, so we use neural network shown here. So in neural network, we have input layer here and output layer here, and hidden layers, several hidden layers, and sometimes bias nodes. And input layer has some input values, and each hidden layer has some nodes shown here. And values of these nodes are determined using values of this previous layer, nodes in the previous layer, and bias nodes. For example, the value here is determined from value of this node, and this node, and this node, and this bias node. And first, we calculate the weighted average. So in the case of this node, some other weight factor is considered. And for this, another weight factor, and this another weight factor. And so we obtain the weighted sum, and then using a nonlinear function called activation function, the value of this node is calculated. And the values of other nodes are calculated in a similar way. The values here, value of this node is calculated from these nodes and also these bias nodes. And then finally output obtained. So in this case, the input information, because of time, I skip detail about this symmetry function. Anyway, that this is information of atomic structure. So this is this corresponds to this input layer, and then that this output corresponds to the atomic energy. So energy of each atom in the system, and then that the total energy of the system is expressed as the sum of this atomic energy. Anyway, so here these weight factors are determined through machine learning. Okay, so next I'd like to explain an example of amorphous lithium phosphate. So of course, first we have to prepare sampling data for machine learning. For this purpose, we consider very small models. This includes 16 atoms, 32 atoms, and 64 atoms. And we performed first principles molecular dynamics simulations. Then we gather the data of the relationship between atomic arrangement and total energy of the model. And we also consider some kind of models, including defects. And we also consider some transient structure that, but because of time, I'd like to skip detail of here, this part. Anyway, in the machine learning, we prepare about 30,000 data. Data means that relation between atomic structure and total energy calculated using first principles method. Then this graph shows a comparison between the energy calculated first principles method and energy predicted by the constructed neural network potential. You can see that most of data are on this line. This means the agreement between the first principles calculation and neural network potential is very nice. In fact, that root mean square error of this case is order of 5 millielectron volts per atom. In the case of this right figure, the similar comparison is shown, but this is for the data structure which doesn't used in the machine learning. So even for the atomic structure, which is not used in the machine learning, the agreement is very nice. And here I'd like to skip this. Important point is we can apply a constructed neural network potential to the system include much more atoms. So as I mentioned, in the training, we use the model up to 64 atoms. But here we apply the neural network potential to a model include about 100 atoms to 1,000 atoms. And it is known in experiments that lithium to phosphor ratio is not exactly 3, but 2.9. So in this simulation, we set the ratio of lithium to phosphor about 2.9. Then the obtained model shows a good agreement with experiments. For example, that in experiments, this P2O7 units are observed, and we can also find such unit in this simulation result. And we also performed the evaluation of diffusion coefficient through the molecular dynamics simulation using the neural network potential and using the largest cell, including 1,000 atoms. This shows the relation between the temperature and the diffusion coefficient. And from this slope, we can evaluate the activation energy for lithium diffusion. And this activation energy agrees very well with the estimate from experiments. So this shows that neural network potential is quite promising for the study of atomic motion in such kind of novel energy and information devices. And we also apply this to the lattice vibration and thermal transport properties. At first, we encountered the problem that even if that agreement on the energy is very nice, I mean that the neural network potential showed very good agreement with fast principle simulation on energy, but still that agreement on phonon property is not good. Actually, this figure shows the relation between phonon wave number and phonon frequency. And so red shows the neural network potential result, and blue shows the fast principle result. So huge discrepancies are seen. But later, we found that if we include the atomic forces in the machine learning processes, I mean that machine learning is performed so as to obtain a good agreement, both energy and forces. Then we can obtain a good agreement on the phonon properties. This shows the phonon properties for silicon, and this shows the phonon properties for gallium nitride. And red curves are result of neural network potential. And the dotted line are result of first principle method. But in many curves, you cannot see the dotted line because agreement is very nice. And this black triangle shows the experimental data. So you can see the agreement on experiment, and neural network potential simulation is also very nice. And then we can also calculate the thermal conductivities. Again, we can obtain a good agreement on the thermal conductivity of silicon and gallium nitride in two different directions between first principle method and neural network potential. So then recently we performed the preliminary simulation on the defective gallium nitride. In this case, we consider the model having where the one nitrogen atom is removed from 32 atom cell. So this is the result for perfect crystal, and this is the result for the model including one nitrogen vacancy. So you can see that the huge difference. So in this way that you can confirm the huge effect of vacancy on thermal conductivity. So we are now trying to improve the quality of neural network potential a little more, and then that we are planning to do more extensive studies on the effect of vacancy and other defects on thermal conductivity. Okay, so this is the last slide, concluding remarks. So in my talk, I explained the importance of understanding on atom ion behavior in novel information and energy devices. And then I mentioned that the first principle simulation is accurate enough to tackle with this problem, but it needs heavy computation. And so under this situation, machine learning approaches combined with first principle data is very powerful and can accelerate the simulation speed without loss of accuracy. And I show that we can construct neural network potential that agree with first principle data. And we show the example of lithium migration in lithium phosphate and the thermal conductivity in silicon and GaN metal. Last part is that if you are interested in the study in Japan, please visit this website. Okay, so actually that the work I presented today in collaboration with these people, former and present member of my laboratories, and with these financial supports and computation resources. Okay, thank you very much for your attention. That's all.
Yeah, thank you very much, Dr. Santoshi. It was very detailed presentation you have made. You have highlighted the importance of simulation compared to the real-time experiments, and you have showed how machine learning and also neural networks can come into picture in simulation. And I'm sure all the students who listen to it would got the basic idea of the difference between the two, real-time and simulation, how cost-effective the simulation is. And thank you very much for that. Now let me open the forum for question and answer session. So faculties and students, if you have any queries, you can ask now.
Sir, Dr. Satoshi.
Yes.
Yeah, I have two questions actually. First one, actually, in this case of silicon, you have mentioned that Weber potential is good. I mean, how do you that conclusion? I mean, have you tried the other potentials possibility of the other potentials?
Okay.
Slide 29, or I think so.
Okay, so actually, that I myself have not examined other potentials, but from this result, that you can see that the good agreement between that neural network potential constructed by our group and first principle simulations, which is on the same level as used in this construction of neural network potential. In the case of empirical potential, it is impossible to obtain this good agreement. And if you obtain such agreement, it's accidental.
Okay, got it. And one more question, Dr. Satoshi. This is regarding LIPO4, Li3PO4. I mean, where do you mentioned it is amorphous. So, I mean, to my understanding, I mean, I'm actually very small in this. I'm starting in the computational science. So, in that, I mean, amorphous, how we will take it? Because if we have to give the atomic positions and everything, I mean, that means it is a crystallite. Suppose if it is amorphous, how you will actually take that into your simulation part?
Okay, so your question is that how to construct how to treat the amorphous structure in this simulation. Is that right?
Exactly.
Okay.
Because
so actually, that to obtain amorphous model, we use simulated annealing method. That means that first we set some initial structure, then heated up the system within the molecular dynamics simulation up to several thousand Kelvin. Then we cool down the system. then we can obtain the amorphous structures. But one problem here is that if the simulation cell is very small, to obtain that truly amorphous like structure is very difficult. I mean that partial crystallization easily occur. On the other hand, if we use a larger supercell, then we can easily obtain that amorphous model. Actually, this figure shows that the radial distribution functions. And in the case of this 100 atom model, that these peaks in radial distribution function, it's a little sharper compared with this case. This means that in this case that a little partial crystallization occurs. On the other hand, in this 1000 atom cell contains much more amorphous features.
Okay, I mean crystallization is not there in the case of large cells. So that is what you are referring.
Yes.
Okay. Sorry, sir. One more. Actually, it is not a question. It is actually a doubt. So both molecular dynamics as well as DFT calculations. I mean, when are you required? For example, if it is smaller in size or less than the atom, you are using DFT, and if it is more than the atom, you are using EMD. Is that right?
I'm sorry that connection is not so good, so I cannot catch you.
Yeah. Can you come up with the question again, Sylvester? Like the is not clear.
Sure, sir. For example, you are using both molecular dynamics and DFT, dense functional theory. When and where you require. When you are actually using DFT and using molecular dynamics.
Okay, so I'm sorry because of time that I skip some explanation.
Okay.
So there are two steps. The first step is that preparation of data for machine learning. For this step, we use both first principles molecular dynamics, and sometimes we also use that molecular dynamics with using neural network potential. Of course, that first principles molecular dynamics is very time consuming. So in this case, that we use only small models up to 64 atoms in
in the last one. LI24. Yeah.
Anyway, that of course that this calculation needs that heavy computation. That first principle calculations. But anyway, once we obtain the neural network by machine learning, then the cost of simulation speed. Sorry, I skipped this slide, but anyway, that simulation speed of simulation using neural network potential is that 1,000 times faster than the first principle simulation. This means that if we perform molecular dynamic simulation of, for example, 60 atom cells, the simulation is 1,000 times faster compared with first principle simulations. But if we consider that a larger cell, for example, 1,000 cell, simulation speed is much faster by the factor of 1,000. I mean that the square of 1,000, so that the factor of 1 million faster compared with the first principle simulation. Okay.
And Dr. Deepak, can I have one more question? Can I have one more question?
Yeah, you can have. Go ahead. Yeah.
The thing is, I know the softwares for this DFTs and the same way molecular dynamics. So, what I mean, which software or otherwise you will choose for? I mean, this neural networks, or I mean, which you can suggest me as a person. I mean, personally, it is not promotion or something, but I'm just asking.
Okay. Actually, in these our studies, we developed our own codes, and one code, the information of one code is available in this paper. And recently, one of my courses released another neural network potential open source software. Unfortunately, that I have not included the information of such code. But very now I'm preparing that some review articles, and I hope that this paper will be accepted within 1 month or so. After that, I can provide that preprint of my review articles, including such information. And for molecular dynamics simulations, and in this study, actually we use our homemade code. But recently, we made some interface between our code and the molecular dynamics code named called LAMPS. Do you know LAMPS code?
I heard. I came through that one.
LAMPS is very efficient for large-scale simulations. So that I recommend that neural network potential and LAMPS software.
Yes, sir. NNPs, right? Yeah.
Yes,
LAMPS.
yes, right.
Yes, sir. Yes, sir. I'm all going through that. Thank you very much, Dr. Satoshi.
Yeah, you're welcome.
Thank you.
Yeah, like we'll take 1 or 2 more questions from others.
I have a question, sir.
Maybe one. Yeah. Go ahead.
Konnichiwa, Professor Satoshi Watanabe. It is an interesting topic. I am Dr. Cyril from Electronics and Communication Engineering Institute.
Thank you. Thank you.
My question is, how will you train the data for material characteristics, especially for transition metal oxide materials? Will you include data from ICSD and JCPDS XRD database also?
Actually, that depends on the purpose of your simulation. For example, in the case of my first topic, the materials was amorphous. In this case, of course, that, to construct the initial structures, we use data from such kind of database. Probably in this case, we use the materials project database. But of course, you can use ICSD data. And in the case of second topic, the target is a crystal. So in such case, of course, we can use ICSD structures to obtain the first structure. And of course, that to gather the data for machine learning, we have to include many data. So that structural data available on the ICSD database is not sufficient for this purpose. I mean that, for example, gallium nitride, such database includes only maybe 10 or at most 100 systems. But in this case, we need that, about 3,000 structures. So that to obtain such structures, we need some kind of additional simulation. For example, molecular dynamics or Monte Carlo simulation.
Thank you. Arigato gozaimasu.
Yeah, you're welcome.
Yeah, any more questions? Maybe one more last question, if there is any. Okay, maybe many will be watching through our Facebook page also. So once they send me a few more questions, I will be happy to mail to you. So I request go through and then send your feedback for those questions as well. And once again, we are very big thanks to you, Dr. Santoshi, and thank you for spending your valuable time and coming today and presenting to our students and faculties. Looking forward to the strong collaboration between Saveetha School of Engineering and University of Tokyo. I can very well see a lot of good discussions coming up today from our faculties. They are very much eager to collaborate also. So maybe in the next meeting we can discuss more on the research collaboration part, or else a joint project proposal. Whatever possible, we can explore that as well. Thank you once again, Dr. Santoshi.
Yeah, thank you. I'm very glad that many people are joining, and also that thank you for getting these opportunities. Thank you very much.
Thank you. Good day.
Good day.